Good morning. We are still reading through the mystery of history. However, we have kind of paused. We're in the mid 1700s with Frederick II and the 7 Years' War. That's in mystery of history, but we've paused to catch up in our science in the age of reason. We had started Lavoisier and his discoveries having to do with combustion. And we said that even your body undergoes a process of combustion with your food to give you energy. Now we're moving on to his work on the conservation of mass. So we will come back to the mystery of history once we catch up with our science, because this science book goes in the order of history as well. So I want to make sure that we kind of see what's going on in science at the same time as the colonies are being established in North America and the 7 Years' War and Frederick II. Okay, so Lavoisier's experiments related to combustion allowed him to discover, we're on page 128 by the way, a very important law of nature. However, to understand this law, you first have to understand a few terms. First one is mass, or first two are mass and matter. Mass measures how much matter is in an object. Matter is all the stuff you are made up of, all the little teeny particles that are connected to make your body. An object, so meaning all the molecules, I guess. Remember, molecules are atoms that are what? Stuck together. Like, so a water molecule uses what type of atoms? No. H2O.
Oh, yes. 2 hydrogen and 1 oxygen.
Yes, 2 hydrogens, 1 oxygen. An object that contains a lot of matter has a large mass. But if it only contains a little bit of matter, then it has a small mass. But you can still be a large object with just not as much mass if the molecules are spread out. Okay, so what is matter? It's a general term for anything that takes up space and has weight. If you think about it, that's pretty much everything around you except for light. Even air has weight.
Air has weight.
Remember, if you blow air into a balloon, that balloon weighs something. Or, remember when we blow up those blow-up beds, how heavy they get? That's because air has weight. We just don't notice it because it's kind of moving all around us.
Yeah, like spread out.
It's spread out, that's right.
Just like the water.
That's true. Water has a lot of weight. On Earth,
It keeps me down. I'm still figuring out how to swim.
You are. On Earth, the heavier something is, the more mass it has. For example, if you look at the difference between a wiffle ball and a baseball, look at the difference between a wiffle ball and a baseball. Which one is heavier?
The baseball.
Yeah, so that one has more mass. Even though they're the same size, it's got more molecules packed into it. Bruce, can you turn off that fan? I feel like I'm talking over a tornado here.
Okay.
Ooh, that's better. Is that better, people?
I think that's better.
Let's see. You can get a wiffle ball that's the same size as a baseball, but if you hold them in your hands, you can immediately tell that the wiffle ball is lighter. This tells you the wiffle ball has less mass, which also tells you less matter. Is mass the same thing as weight? No. Mass measures how much matter is in the object, while weight measures how hard gravity is pulling on you. So if you weigh 80 pounds, that tells you the Earth is pulling on you with a force of 80 pounds. If that is your weight on Earth, your mass is 36,287 grams. If you aren't familiar with the term gram, it's a unit. That's how we measure mass.
I know grams. That's in my math book.
It's kind of like pounds. It's just a way that we measure things, or of like, I need 1 cup of milk. A cup is what we're using to measure how much milk we need. Let's see here. Ooh, the air turned off now. I really feel like we can hear. To give you an idea of how much a gram is, a $1 bill has about the mass of 1 gram. So that means if we rarely ever have cash on us anymore. Daddy used to carry it till before COVID, but now after COVID, hardly anybody carries cash. But a dollar bill weighs about 1 gram. If you went to the moon, your weight would be less because the moon's gravity is not as strong as the Earth's gravity. You'd weigh only about 13 pounds. If you were 80 pounds on Earth, you'd only weigh about 13 pounds on the moon, but your matter would not change.
That's pretty cool.
Well, for your matter to change, you'd have to lose some of your body, and that's kind of gross. Well, I guess if you lose some hair, if you cut your hair off, then you've lost some matter.
Yeah, since you have to cut your hair and then it doesn't get to you.
Or your fingernails, clip your fingernails.
I actually did, but I never did any bald.
Now that you understand what mass is, you can understand the law that Lavoisier discovered. Let's start with an experiment. It uses a chemical reaction that you've already done. Let's see, we're going to skip over the experiment. Let's see what it said. Okay, it says you put pull steel wool into long strands, stuff them into a bottle. Use a knife to push them into the bottle. Fill it about 3/4 full. Do that in 2 bottles. Add vinegar to 1 bottle until it covers the wool, and then do that for the other bottle. Dump the vinegar out of both bottles into the sink, then rinse the entire sink with lots of water. Put the opening of the balloon over only 1 bottle. Let the 2 bottles sit overnight and make sure the lights in the room stay on. The next day, examine the bottle's opening. What does the balloon look like? Examine the steel wool. Don't pull it out, just rotate the bottle. Do you notice a difference? Okay, first you should have seen that the balloon got sucked into the bottle. This really shouldn't have surprised you. After all, Cruz, that's really loud, babe. After all, you did a similar experiment in Lesson 35, and it sucked water into the bottle because the steel wool rusted, because it reacted with oxygen and air. That pulled oxygen out of the air and had to be replaced. But what did the steel wool look like? In the bottle with the balloon, it should have been nearly as rusty it was in the bottle without. It should not have been nearly as rusty in the bottle without the balloon. The steel wool was rusting, which meant it was reacting with oxygen. That took oxygen from the air. In the open bottle, more air rushed in to replace the missing oxygen. So new oxygen was brought into the bottle. The bottle that had the balloon on it couldn't pull in any more air, so it stopped the oxygen from coming in. The amount of oxygen the steel wool had to react with was less. This meant that the steel wool in the balloon-covered bottle could not rust as much as the steel wool in the uncovered bottle. Okay. It was. It was just saying that Can you get a squishy guy, please? Because those Legos are making a whole lot of noise. Yeah, get 2 for you and 2 for Kale. It was just saying that the balloon was preventing oxygen from touching the steel wool, and so the bottle with the balloon on it, the steel wool wasn't as rusted. So Lavoisier did similar experiments to this. He was reacting chemicals with oxygen by burning them and carefully measuring the mass of the chemical, the mass of the air, and the mass of the air that was available to the metal. And he measured the mass of the results. He found that after the reaction, the metal gained just as much mass as the air lost. So even though the metal changed, and even though the oxygen was pulled out of the air, the total mass of everything didn't change. So what he's saying is, let's pretend he did an experiment inside a container. He did not open the container. There's air in the container. There's metal in the container. He added a chemical inside the container to cause the metal to burn. But he keeps He adds the metal, the chemical, and the air, but he keeps the container closed. He's saying that even though the metal burned up, the total mass for the air, the metal, and the chemical stayed the same. Let's draw a picture.
Okay, I'll get you some paper.
Just get a piece of paper and a
I mean, I get what you're saying, but I don't understand why it still weighs the same.
okay. So Cal, let's draw a picture. Here's our container. He's doing an experiment. Got a container. Now we know that air has mass, meaning the air has molecules in it and it has weight. So here are the molecules in the air. He adds a piece of metal. Let's count how many molecules that is. We're just pretending. It's just, obviously it's much more, but let's just pretend there are 1, 2, 3, 4, 5, 6, 7 molecules. And he is going to burn this metal paper clip that has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 molecules. And he's going to add a chemical. So he's going to then pour, before he shuts the lid, he's got a lid on here. But before he puts the lid on, he's going to measure how much of the chemical, he's going to add this chemical. 1, 2, 3, 4, 5 molecules. He puts the lid on, and he knows how much air he has, how much the paper clip, what the mass is of the paper clip, and the chemical. Well, as soon as that chemical touches this paper clip, it starts to burn. Okay, so the chemical loses molecules because it's burning. But what it's reacting with this, so let's just say it loses a molecule. But if this loses a molecule, this is going to gain a molecule. Okay?
Yeah, so if it loses a molecule, it gains a molecule.
The amount of matter stays the same in the container, whatever it is. Let's say the air. There's smoke that's going into the air from this chemical reaction. Well, that smoke is pulling molecules off of this paper clip because it's burning. So it's going, these molecules are going out into the air.
But the molecules aren't destroyed, right?
They're not destroyed. They might be changing by a chemical reaction. The amount of matter is the same. So it might be a different type of molecule now. Might be a smoke molecule. So now let's just, our smoke molecule, we've got this. 2 smoke molecules went here. Okay, so now that's in the air. And let's just say we've got some ash from burning that fell off the thing that goes onto the ground here. Down here. We've got ash that went down here. Let's do 2 of those down there. Oops.
Since you showed that there's one of those orange molecules had been destroyed, but
this one gained it. So the chemical reaction, it added something to the metal. So it's not destroyed, it's just changed. So it's no longer this chemical. It's added a different type of matter to this. So a chemical reaction could change the type of molecule.
oh,
But the amount of matter, so here's our matter, stays the same. So let's count how much we have left. We started with, see, that one went, that one went, that one went, that one went. All right, we started with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, I lost count.
I can count. Like, you want all of them? Like, I can count.
Let me count these first. That's 5. We had 5 molecules for the chemical. We had 1, 2, 3, 4, 5, 6, 7 molecules. Is that right? From the
Yes.
air. And on the paper clip, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, that's 12 plus 12 is 24. Okay, so we should still have 24 molecules because the amount of matter stays the same.
Wait, oh.
So, because this lost some because it burned. It turned into ash and fell onto the bottom of the bucket. This lost some because it burned and it changed the paperclip and added some things to the paperclip. And then some changed into smoke into the air that's in the container. So now let's see how many we have now. Now we have 4 left in the chemical. We have 2 down here on the ground. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 still on the paperclip. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 plus 9 is 18 plus 6 is?
1 second, that's 24.
24. So our matter, what he's just saying is that, here, let's turn the page so we can see the exact what he said. When substances change form, this is the law of conservation of mass. The substances change form. The total mass is neither created nor destroyed. It stays constant. So you can't create or destroy matter. Is that right? The mass, the total mass. The English translation of his words is nothing is lost, nothing is created, everything is transformed. So it's just transformed into something else. Let's see, Lavoisier helped us understand so much about chemistry that some call him the father of modern chemistry. So you can't destroy the matter. Do you see what I'm saying?
Yes.
It can be transformed into something else. From air to smoke, or from a chemical to that can add something to the metal or burn the metal and turn it into ash, but you cannot destroy matter. It can be transformed into a different kind of matter. What was the other thing that we couldn't create or destroy? Do you remember?
Electricity.
Close. What is electricity a type of?
Energy.
Energy, yeah. So, despite everything that he did, Lavoisier had a tragic end in his life. During the Reign of Terror, which was a period of violence that occurred during the French Revolution, he was executed because of his close ties to the government. The Revolutionary Tribunal said he was a part of a conspiracy against the people of France. When he heard about this, the French mathematician Joseph Louis Lagrange remarked, he said, it took them only an instant to cut off that head, and 100 years may not produce another like it. So he was just lamenting. He was just being sad and just saying, I can't believe you have done that to him. He was a brilliant man who was helping us with science. So the law of the conservation of mass tells us that you cannot create matter, and you cannot destroy matter, but you can do what?
You can transform it.
You can transform it. Now, mass is not weight. Weight measures how hard gravity is pulling on you, but what does mass measure, Cruz?
Mass measures how much, I forget.
Matter is in a thing.
Oh.
Measures the amount of matter. How many molecules and everything is in your body? That's your mass. Your mass doesn't change if you go to your moon, but your weight will change because the amount of gravity that's pulling on you will change. All right, that's it for today with science in the Age of Reason and Lavoisier. We have Lavoisier again in lesson 43 next time, and he is going to be talking about elements, and then we'll move on to Luigi Galvani. All of these are in the mid-1700s, so I want to do a few of them before we move on to the 7 Years' War. All right, have a good day. Goodbye.